Christian Berglund with his late 19th century experiment, Torella. Searching for an explanation to the aurora phenomena, he stumbled upon the secrets of the universe. His model of the sun, the real sun. Hydrogen to helium fusion has never been accomplished in nature or a laboratory. The sun cannot be some kind of internal furnace. This would violate the second law of thermodynamics. This would mean that the energy from the sun must come from outside the sun, not inside the sun. The aurora phenomena creates more electricity than the top 8 power generating plants on the planet Earth. Now let us observe the electromagnetic forces at work. Now let us study the Ptolemaic universe and why was it incorrect. It was incorrect because it had to invoke metaphysical properties to explain the observational data. You must study history or you are doomed to repeat it. The universe, according to the Big Bang Theory, invokes more metaphysical properties than the Ptolemaic universe.
When Einstein proposed this, it's a theory of gravity, which means that it's a theory which should represent the whole of the universe, because it's gravitational forces that are controlling the universe. Well, Einstein made this theory around 1915, and he immediately wanted to try and use this theory to explain the universe as it then was, the so-called Milky Way system. But of course, the idea of this was that it was a static system. That is, it wasn't contracting or expanding, it was a static system. And Einstein found that his equations did not allow for a static universe unless he inserted a certain constant in the mathematics, which became known as the cosmological constant. But what happened in the early 1920s was that a very clever Russian called Friedman in 1922 found solutions to Einstein's equations which allow the universe to either expand or contract. Now that was done in the Soviet Union soon after the revolution, and nobody in the West knew about this, I think. But in 1927, a Belgian priest, the Abbé Lemaitre, as he later became, also discovered these solutions. And he went to England, and his work was publicized in Cambridge and elsewhere, and the famous English astronomer Sir Arthur Eddington and others got to know about this, and they immediately began to say, how can this apply to the current universe? Well, in the same period, in 1929, Hubble made what I still believe was the most important discovery in extragalactic astronomy in the last century, or the last century but one. He showed that if you look at the spiral nebulae, the faint spiral nebulae, the shifts in their spectra are proportional to their apparent brightnesses. And this led very soon to the idea that this fitted very well with the expanding universe, and that indeed this is the kind of universe we lived in, that what we were looking at are galaxies, Milky Ways, further and further away from us, and the further away from us, the larger the redshifts, and if that's interpreted in the way that most people would interpret it, this means
Edwin Hubble, meet Helton Arp.
When Hubble made his great discovery, It was for galaxies like our own Milky Way galaxy, and they all followed the same rule, that the fainter they are, the larger their redshift. In other words, the faster they are moving away from us. This is known as the Hubble law, and directly led to the expanding universe theories. But in the 1960s, there was a new discovery, the quasi-stellar objects, often referred to as quasars. They appear as star-like points on the sky, frequently blue in color, and they have very, very large redshifts, implying that they are at huge distances from the Earth, at the very boundaries of the observable universe. Some astronomers soon found that a vast number of these strange new objects populated the regions around spiral galaxies, and were not only observable with radio telescopes, but were optical and X-ray sources as well. There were two properties of the quasars that were difficult for astronomers to understand using the expanding universe theory. The first was that if one plotted their apparent brightness against their redshifts, as one does for galaxies, one gets an unexpected scatter on the diagram, instead of the smooth curve made by the same plot done for galaxies. This seems to indicate that the quasars do not follow the Hubble law as do most other objects, and that there is no direct indication that they are actually at their proposed redshift distances. In fact, it is argued that if Hubble had first been given the plots for quasars, he and other astronomers would never have concluded that the universe was expanding. The second property was that quasars are very small, compact objects, sometimes only a light year across. So if quasars are really at their extreme redshift distances, they must then be the brightest and most energetic objects known to astronomers. So energetic, in fact, that untestable, almost metaphysical mechanisms must be applied to explain the phenomena. On the other hand, when placed at their observed distances, peculiar galaxy NGC 7603, discovered 30 years ago by Halton Arp, is one of the more striking examples of galaxy-quasar connections. It has recently been re-examined after the discovery of two new quasar-type objects embedded in the connecting filament.
Now, this may not sound like much, but in energy density, where we measure the absolute differences, the differences is 4 orders of magnitude, 10 times 10 times 10 times 10 difference.
Although Big Bang advocates claim the discovery of the cosmic microwave background radiation as conclusive proof of their theory, history actually shows that there is a long line of well-hidden predictions previous to those made by Big Bang theorists. Not only were these predictions prior to those of Gamow and associates, but more importantly, they were made without any need for an expanding universe, and with far greater precision. This shows us that observations such as the background temperature of space have no preference for one or another theory, and therefore may not be used as definitive proof of any particular model. The fact that a theory is able to describe an observation does not mean that the observation proves the theory.